Hello everyone. This is the final presentation for Project 2124, part of summer of HPC 2021. We are Iakov and Adrian, and this summer we have been hosted by Hershey Center in the UK and mentored by Vasil Alexandrov and Anton Lebedev. So let's start with the background for our project. The generic form of problems that we focus on is what's called a system of linear algebraic equations, and it's quite simple in its definition. These systems come up in majority of scientific fields, from economics to engineering. The ability to compute the inverse of A has special significance because it then becomes easy to solve for X. A common approach for this is an iterative solver, but as we begin considering problems of larger scale, that approach can become prohibitive because it is too computationally expensive. Preconditioning is an alternative approach that our project is based on. It transforms the problem so that it can converge to a solution faster. The difficulty with preconditioners is that finding good ones is not trivial. There is no rigorous mathematical approach that can provide an optimal preconditioner for a given system. Our aim is to devise an algorithm that can make good guesses for input parameters of Markov chain Monte Carlo matrix inversion method, which computes the preconditioner. Next, we'll introduce the algorithm that performs the parameter optimization.
The algorithm design is determined by a set of limitations. First of all, we have little initial knowledge of what to expect from the models, which makes a flexible model important. This also ties into the problem where we have a very expensive sampling, as we have to make the maximum usage of each data points, storing it and ensuring that the sample is taken in the most optimal area. The general idea is therefore to build a statistical model at the same time as you do the sampling, which is iteratively updated to be more and more true to the real model. As shown in the picture, this leads to four important components: data storage, a statistical model, an optimization of this model, and an evaluation in the real system. In the end, we hope that the maxima of the model converges towards the real maxima. We coded this in Python, as this is mostly an investigative project, meaning performance is less important than fast development time and easy understanding. We are also heavily dominated by sampling time rather than own code, and this might be interfaced towards C code. As for the statistical model, we decided on using Gaussian processes, which return a probability distribution of the most likely functions fitting the given data. Choosing the most likely function gives a well-behaved nonlinear fit to the data. Another benefit of the Gaussian processes is that their gradient is easily calculated, meaning that we could naively optimize by moving towards the point in an increasing direction. Finally, for the evaluation, we calculated the inverse with and without preconditioner and calculated the ratio between these times. This allows us to put matrices with different solving times and data points computed with different amounts of resources in the same model. Let's see how well this performed.
So, as it's evident from the plots, the algorithm does not perform particularly well. It converges to some set of parameters, generally within 10 samples, but the reward does not increase. This graph includes multiple runs for a set of 6 different matrices. We therefore focused our attention towards finding the errors leading to this behavior. The first obvious error is the appearance of outliers with a much higher reward than plausible. As seen in this plot, very similar parameter values do not perform nearly as well. These cases appear to happen when the load on the computation nodes changes during the evaluation and must be removed as they skew the model heavily. Second point is that the algorithm is biased towards initial samples. It does regression with a small number of points and therefore favors exploitation over exploration, causing it to find local maxima instead of global. This speaks towards adding more randomness into the point sampling rather than just finding maxima. Lastly, in some cases, the fitted surface is too smooth. Such distributions of samples with low reward, as illustrated here, make it difficult to produce a realistic and detailed surface. Gaussian processes are very flexible, and we believe that more experimentation on larger datasets would yield more suitable models.
One step towards a more general algorithm would be considering matrix features, such as matrix norms, approximate eigenvalues, minimum and maximum entries of the matrix, sparsity, and symmetry. They could be used to build a model that has matrix features as another dimension and allows inferring optimal parameters for similar matrices. In this project, we considered 6 sparse matrices, but such modification would require more data and larger matrices. As you can see from the plots to the right, our initial exploration of matrix features did not reveal any correlations for a given dataset. Thank you for listening to our presentation.